Okay, hello everyone. My name is Chanyoung Kim, who is the PhD student in Ulsan National Institute of Science and Technology in South Korea. And today I'd like to have a presentation about the seismic fragility analysis of nuclear reactor concrete containment considering Alkali-Silica reaction. So this presentation will follow the orders as shown in here, and I'd like to start from the introduction. So for the seismic fragility analysis of the structure in nuclear power plants, the guidelines suggested by Electric Power Research Institute have been used for many decades. And for the containment structure, the shear strength equation suggested by Ogaki et al. In 1981 is commonly used. So in this methodology, the nonlinear behavior of the containment structure is simplified using effective shear area or the inelastic energy absorption factor. So in recent studies, many researchers have been conducted nonlinear time history analysis and tried to using appropriate damage index such as damage parameters or the drift level of the structure. And in current guideline, it is suggested that the concrete compressive strength increased by time should be considered for the assessment. However, the evaluation guidance for the degradation in the concrete is not enough. And in 2010, the symptom of Alkali-Silica reaction was first reported in several plants. So it is well known that the expansion and microcracks due to the Alkali-Silica reaction could decrease the structural capacity. So this study is focused on conducting seismic fragility analysis with the appropriate damage index for the containment structure, and also try to evaluate the effects of Alkali-Silica reaction on the containment structure. So next chapter is about the finite element model and the ground motion. So the target structure is the containment structure of the nuclear power plant typically used in Korea, and OpenSys version 3.3 is used for the analysis. So for the configuration, we used multi-layer shear element developed by Wu et al. At 2015. And this element using lateral shear section, which was composed of several layers for the concrete and reinforcement. So for the concrete constitutive model, we used plane stress usual material developed by same authors for the shear element. And it is composed of tension damage model of Roland and compression damage model of Majors. So to validate this finite element model, we tried to compare it with the experimental result of Kato et al. At 1981. And this experimental result is used for the reference for the shear strength equation in the current guideline. So we tried to develop the static cycle analysis result and try to compare with the experimental result as is shown in the right figure. So in terms of the relation between the drift level and the average shear stress, the analysis results are well met with the experimental result, and we decide that this element model has enough validity. Thereafter, we try to develop the input ground motion. So at first, we conduct spectral matching process, and thereafter we select 30 AutoCAD time series sets. So the target response spectrum is the response spectrum suggested by Direct CR0098, and the ground motion selection is based on the SRP 3.7.1 guideline, which was suggested about the ground motion incoherence. So next is about the Alkali-Silica reaction model. So as it aforementioned, the symptoms of Alkali-Silica reaction was firstly identified during the license renewal of the Seabrook plant around 2012. And actually, the Alkali-Silica reaction is the reaction between the siliceous aggregate and the alkali contents in the cement. So it will make the Alkali-Silica reaction gel, which will absorb the water, and this water imbibition will result in expansion and microcracks. So finally, the concrete material properties will be decreased. So many constitutive models have been proposed to simulate this behavior, and in this study, we adopt the model suggested by Saoma and Perty at 2006. So in this model, the ASR strain is defined as the function of time, temperature, humidity, stress state, and activation energy. So we try to combine this model with the plane stress usual material, try to input the calculation of Alkali-Silica reaction expansion and degradation due to expansion. So thereafter, we try to validate this model with the experimental result from the other researchers. So this is the experimental result of Gautam at 2016. And firstly, we try to compare the result and calibrate the parameters with the cube specimen with no confinement. So we calibrate the latency time parameters, characteristic time parameters, and the maximum volumetric strain as it presented in this slide, and try to using the same parameters for the other specimen with different confinement condition for the uniaxial confinement or the biaxial confinement. So the evolution trend and distribution of the strain in each direction is similar with the experimental result. And finally, we tried to compare the analysis result with the report about the Seabrook plant. So actually, we do not know exactly about the geometry of the Seabrook plant and some reinforcement detail of the Seabrook plant. So just using the same finite element model for the Korea nuclear power plants, but just try to compare the strain level with the reported value. So in the analysis result, as you can see, the strain in the meridional direction, which means the vertical direction, is about 0.0148% in the first floor. And for the hook direction, it is about 0.0072% in the first floor. So there is some little bit difference with the reported value, but we decided that this level is very similar and try to using this for the further analysis. And in terms of the maximum base shear, it is decreased about 4.3%, and drift at the maximum base shear is decreased about 14% when the Alkali-Silica reaction is considered. Next is about the fragility analysis methodology. So in this study, we're using the methodology suggested by EPR TR 103959 guideline, the study of Choi et al. 2008, which was dealing with the fragility analysis on candle containment structure. So in this methodology, the uncertainties of parameters are considered using logarithmic standard deviation, and EPR guideline suggested about some reference value for the standard deviation. So in this study, we're just considering about the uncertainties in damping frequency and the concrete compressive strength. So Latin hypercube sampling method is applied to develop the 30 analysis sets. And next is about the estimation on the uncertainties of seismic demands. So in this step, we're using 30 earthquake time history sets and using finite element model, but for this model, we set all the parameters as the median value, so we assume that the analysis results are only affected by the randomness of earthquake. And in next step, we try to estimate the uncertainties of seismic capacity, so we combine 30 earthquake time histories with the finite element model analysis sets developed by Latin hypercube sampling. And in this step, we assume that the seismic capacity is only affected by the uncertainties of structural parameters. And next is about the consideration of Alkali-Silica reaction. So actually, the ASR model we developed is not yet fully validated for the dynamic analysis. So instead, we just modifying the material properties a little bit and try to modifying the change in material properties. So the fragility curves will be developed by the following equations in this slide. And next is about the resultant discussion. So when the Alkali-Silica reaction is not considered, the seismic demands could be expressed as a polynomial fit in this slide, and the maximum drift at the horizontal direction is assumed to be the seismic demand in this study. So beta from all results are it's about 0.1833. Next is about the seismic capacity. So in the left figure, we can see that the drift level is still increased as the PJ increase, but in the right figure and the middle figure, you can see the drift level at the maximum base shear is not increased beyond a certain PGA level. So we assume that the maximum drift at the maximum base shear cycle could be used as some index for the seismic capacity. And we try to using this index for the fragility analysis. So the median seismic capacity as the drift level is about 0.4405%, and beta U from all results is about 0.3294. So it is close to the generic value of 0.32 suggested by Choi et al. At 2008. And thereafter, we try to estimate the uncertainties of seismic demand and seismic capacity when the Alkali-Silica reaction is considered. So the median seismic demands could be expressed as polynomial fit in this slide, and beta from all results is about 0.2093. Thereafter, the median seismic capacity is estimated by the same damage index, which I was talking before, and the drift level is about 0.4067%, so it is decreased about 10%, and beta from all results is about 0.2843. So by using these beta values, we develop the fragility curves and try to compare it with. So the median capacity for the containment structure when the Alkali-Silica reaction is considered is decreased about 20% when the Alkali-Silica reaction is not considered. So this is the conclusion. So when in the ASR analysis for containments show that the strain level is lower than 0.015% in both hoop and meridianal directions. So this level is similar with the reported value from the Seabrook plant, which was reporting about 0.013% in both directions. And in the static in the cyclic lateral load analysis after the ASR analysis, the containment showed the maximum base shear and the drift at this point is decreased about 4.3% and 14% respectively. So when we try to use the damage index based on the drift, the median capacity of the containment structure is about 3.279 G, and Heathcliff is about 1.407 G, which was very similar with the previous reported value. And the median capacity decreases about 12% when the effects of Alkali-Silica reaction is considered as change in material properties. So in future works, we try to using the developed ASR model and try to develop the fragile curves with that model. So this is the end of presentation, and thank you for all the attenders in this presentation.